Welcome. Welcome to the Plasma Physics course of TPFL. Today we are going to talk about the single fluid description of a plasma and the MHD model. In the past lecture, we have seen that it's possible to describe the plasma dynamics with a two-fluid model, basically describing electrons as ions as two different fluids. Today we will provide an even simpler description, the one that is able to describe the plasma dynamics as the evolution of one single fluid. So, as a first thing with you, I will briefly recall the main elements of the two-fluid model. Then I will introduce the variables that are considered by a one-fluid model, and I will describe this model. And finally, I will describe what are the typical assumptions that are made into the one single fluid description of a plasma to come up with the magnetohydrodynamic MHD model. That is one of the most common used models in plasma physics. So let's briefly recall the main elements of the two-fluid model. Within the two-fluid model, the dynamics of each fluid is given by a continuity equation. That is, the time derivative of the particle density is due to the particle flux. A momentum equation, which states that the time derivative of the plasma velocity is due to the forces that are acting on this fluid element. That is the electric force, magnetic force, pressure forces, and friction force. With d over dt, we have made the convective time derivative, that is, and the friction forces are given by the integral of the collision terms of Lazo into Boltzmann equation. The pressure term is given by a closure equation that I am not going to write here. And the system has to be coupled to Maxwell equation. Let's state that divergence of E is equal to rho over epsilon 0. Divergence of B is equal to 0. The curl of E is minus dB over dt. And curl of B is given by the current. And time derivative of the electric field. Charge density and current density are related to the two fluid quantities by fact that rho is given by the sum over all species of the charge of each species times ns, the density, and the current density is given by the sum over all species of qs, ns, and us. This is the two-fluid model that describes the dynamics of a plasma, taking into account the dynamics of electrons and ions as two different fluids. Starting from the quantities such as ns, us, quantities that are relative to each species, we can actually deduce the one fluid quantities that are evolved by the one fluid model. The first quantity of interest for the one fluid description of a plasma is the mass density. We will denote it as rho capital M. It's a function of space and time, and will be given by the sum over all species of the density of each species times the mass. And if, for example, there is one single ion species in our model, this will be given by the sum of the electron contribution plus the ion contribution. Another quantity of interest is the center of mass velocity. We will denote it with a capital V, and it's still a function of space and time, and will be given by the ratio between the velocity of all particle species weighted according to their density and their mass, normalized to rho m, that is ns ms, and the sum is over all species. And this, for example, for a single ion, for a plasma with a single ion species, will be given by the sum of the electron contribution and the ion contribution divided by the total mass. Then there are the quantities related to the total electric charge and total electric current. We have somehow already introduced those in the previous slide. That will be still called rho, that is the sum over all species of NSQS. And for the case of one single ion species that is ionized only once, this will be given by E Ni minus Ne. And for the current, we will have similarly the sum over all species of the current carried by each species. The last quantity that we want to introduce is the pressure in the center of the mass frame. We first define the pressure in the center of mass frame for each species. That is a tensor. And differs from the standard definition of the pressure because the US has been replaced by the V, the center of mass velocity. And starting from the center of mass pressure of each species, we can get the total, the one fluid variable, the total pressure in the center of mass, that is given by the sum over all species of PSCM, that in the case of one single ion species will be given by the electron and ion contribution. We now have all the elements to deduce the one fluid model of a plasma. Let me just point out that in this derivation we will stop at the level of the momentum equation. For the energy equation we will use a simple closure. So let's see how we can deduce the model, the one fluid model that describes the plasma dynamics. To do that, we can start from the continuity equation for the electrons and for the ions. We can now multiply the electron continuity equation by Me and the ion continuity equation by Mi. Sum up these two equations, and if we do the calculation, what we obtain is an equation for the mass density, where V is the center of mass velocity. Similarly, we can multiply the electron continuity equation by the minus E, the electron charge, and the ion continuity equation by E, the charge of the ion species. Sum them up, and what we obtain is an equation for the charge density. We can use a similar approach to deduce the equation for that evolves the plasma at the center of mass velocity and the current. The starting point in this case are the electron and ion momentum equations. We can sum up these two equations, and what we obtain is an equation for the center of mass velocity that takes into account the electric forces, the magnetic force, and the contribution of the pressure term that is actually written in terms of the center of mass pressure. And in order to obtain an equation for the plasma current, we should multiply the electron momentum equation by 1 over E and E with a minus sign, and the ion momentum equation by 1 over E ME over MI and I, and sum them up. We think the hypothesis that our plasma is quasi-neutral, and we will call it the electron and ion density, which are very close, as N. Also in the hypothesis that ME, the electron mass, is much smaller than the ion mass, and that the current is much smaller than the current carried out by each species. We will have an equation for the electron current that states that the time derivative, this convective time derivative of the electron current is due to the electric field, a V cross B term, which represents basically the contribution of the electromagnetic forces, a term that is related to the pressure tensor, and a resistivity term. We can now summarize the equation for the one fluid model. It will be made up by a mass continuity equation, a charge continuity equation, a momentum equation, and an equation that states how the current density evolves. We can call it Ohm's law. And this has to be associated with a closure equation. For example, if there are sufficient collisions, then we can assume that the pressure tensor is actually a scalar, and therefore d over dr, divergence of the pressure tensor, becomes the gradient of a scalar that we will call P, and P will be given by a state law, state of equation law, where gamma can be equal to 1, for example, and in this case we have isothermal plasma dynamics, or can be equal to Cp over Cv for an adiabatic motion, or gamma can be equal to infinity in the case of incompressible flow. The system is then completed by Maxwell equations that, as usual, read as divergence of E equal to rho 0, divergence of B equal to 0, curl of E equal to minus dB over dt, and curl of B equal to the contribution of the current. What we have just written here is a closed system of equation. It's a closed system of equation that describes the dynamics of a plasma as the evolution of one single fluid. Even if the model that we have just described represent a substantial simplification with respect to the kinetic model and the two-fluid model, sometimes it's too complicated and it's not possible to treat it analytically and numerically, and therefore some assumptions are done in order to make the problem more tractable. Let's see together what are the typical assumptions that are done. there are actually 4 assumptions that are done. The first assumption that is typically made is the one of negligible electron inertia. This means in practice to take the limit of the electron mass that goes to 0. In other words, what one does is neglecting this term here. The second assumption is to assume that the plasma is quasi-neutral, which means to consider phenomena that occurs on scale length that are much larger than the Debye length, phenomena that have typical frequencies much smaller than the plasma frequency, and that have a frequency much smaller than the ion cyclotron frequency. Under this assumption, one can impose that the charge density with respect to the density of the electron is that is equal to the ratio of the difference between the electron and the ion density divided by the electron density has to be much smaller than 1. In practice, what this means is that we can neglect the rho over E term into the momentum equation, the d rho over dt term into the charge continuity equation, and also the Gauss law becomes an equation that we cannot use anymore to evaluate the electric field. The third hypothesis that is done is to neglect electromagnetic waves. That is to assume that the displacement current is much smaller than the plasma current. This means in practice that we can neglect into the Maxwell equation the displacement current, and if you look here, what we will have is that the divergence of J will be equal to 0 all the time, as the divergence of B, of curl of B, is equal to 0 all the time. Therefore, this means that the divergence of J is equal to 0, which in practice tells us that also this term in the charge continuity equation can be neglected. The last hypothesis we do is to assume that the phenomena that we consider occur on scale lengths that are much larger than the Larmor radius. This, in other terms, means that the V cross B term is much larger than the term due to the pressure. And therefore, into Ohm's law, we can neglect the pressure term. What you have just obtained is the so-called magnetohydrodynamics model, MHD in short. Is one of the most widely used models to describe the dynamics of a plasma, and you will use it throughout the rest of the course. So it's important that we write together all the equations that constitute this, the MHD model. The first equation is the continuity equation for the mass density. That is the mass density varies in time according to the particle flux. The second equation is the momentum equation. We state that the center of mass velocity changes because of the J cross B force and also the gradient of the pressure. Then we have Ohm's law, that with the simplification we have done got reduced to E plus V cross B equal to the resistive term. Then there is a closure equation, which in the simplest form can be written as d over dt of of the pressure times the mass density to the power of minus gamma, where gamma is the index of the polytropic, equal to 0. And all this has to be coupled to Maxwell equations that in the simplified form we are looking at can be reduced to curl of E equal to minus dB over dt, curl of P equal to nu 0 j. We have neglected the displacement current, and divergence of B equal to 0, which as Maxwell equation always say, this is to be considered an initial condition of our problem. Well, so how many equations and how many unknowns do we have? Let's try to summarize these. So the unknowns are rho m, v, j, b, pressure, and the electric field. 14, if we count, 14 unknowns. One plus 3 plus 3 plus 3 plus 1 plus 3. 14 unknowns. And how many equations? We have 1 plus 3 plus 3 plus 1 plus 3 plus 3. 14 equations. What we have obtained here is actually a self-consistent model that is able to describe the plasma dynamics. Now let me point out that if the plasma is sufficiently hot, then the resistivity can be very small and can be neglected. In this case we will talk about ideal MHD model. Otherwise we will talk about resistive MHD model. The MHD model is particularly suited to describe the global dynamics of a plasma. For example, it's widely used to describe the dynamics of a plasma in devices that are used to confine plasma for fusion purposes. And here is the result of one MHD simulation that has been run by our group here in Lausanne to study the equilibrium magnetic field in the W7X experiment. This machine in Germany is one of the largest experiments on Earth and uses a complex three-dimensional configuration to confine plasma for fusion purposes. And here we got to the end of this lecture. What we have done today was to derive one single fluid model to describe the plasma dynamics. More particularly, what we have done was to introduce the one fluid variables and the equation that evolves them. And then we have seen that by making a number of assumptions, in particularly by neglecting electromagnetic waves, Larmor radius effect, electron inertia, and assuming quasi-neutrality, a model, the so-called MHD, magnetohydrodynamics model, can be deduced. And this is one of the most fundamental models used in plasma physics.